light and matter in general. We're
Yeah.
getting specific. We're talking about what happens when they, well, collide with enough energy to actually kick an electron right out of its orbit.
Mm-hmm.
We call that electron a photoelectron, and the whole process, that's the photoelectric effect.
Right. And it happens all over the place. Solids, liquids,
It's even gases, you mentioned.
even gases, yeah.
Yeah.
So prepare for a surprisingly fundamental journey, I think.
I like that. And it's fundamental because, as you said, it's not just some dusty old physics concept, is it?
Not at all. I mean, the fact that light can dislodge electrons, it's like a key. It unlocks how we understand, well, pretty much everything from the tiniest particles up to some really advanced tech.
Okay.
So our goal today is to really, get to grips with these photoelectrons, how they're born, what makes them tick.
And why they matter so much.
Exactly. Why their existence has such a, profound impact on science and, frankly, our daily lives.
Right. We've got some really interesting info lined up here. We'll dive into the science, the nitty-gritty, and then come up for air with some pretty mind-blowing applications.
Sounds good.
So, where do we start? The science behind these ejected electrons. How does it all begin?
Okay, well, the story really kicks off with this phenomenon that, frankly, baffled scientists for quite a while.
Right.
Until Albert Einstein, in that amazing 1905 paper of his.
His miracle year, yeah.
Exactly. He provided the explanation, the photoelectric effect. And this insight, it was so pivotal, it later won him the Nobel Prize.
Wow.
It basically describes how a photon, which you can think of as a tiny packet, a quantum of light energy, hits an electron inside a material and bang, transfers its energy.
Okay, so it's a bit like playing pool. A light particle hitting an electron ball.
Sort of, yeah.
Yeah.
It's a decent analogy to start with. But like you hinted, it can't be just any light hitting it, right?
Right. There has to be enough energy involved.
Precisely. Think of the electrons as being kind of stuck in an energy well. To get out, to escape, they need a certain minimum amount of energy, a boost, to climb out of that well.
And that minimum energy.
Yeah.
That has a name.
It does. It's called the work function. You'll often see it written as the Greek letter phi, or sometimes just W.
Phi or W. Got it.
And the key thing is, it's unique for every material. It's a specific property, like, density or melting point.
So different materials hold onto their electrons more tightly, basically.
Exactly. Some let go easily, some need a much bigger energy kick.
Okay, so how do we know if a photon, our light particle, has enough oomph, as you put it? Does that depend on the light itself, like its color?
You're right on track. It absolutely depends on the light's properties, specifically its frequency and wavelength. They're related to the photon's energy.
How so?
Well, the energy E of the single photon is directly proportional to its frequency. F, higher frequency, leads higher energy.
Like UV light compared to red light.
Perfect example. UV has a higher frequency, so its photons pack more punch. The equation is E equals HF.
EHF, I remember that one. H is Planck's constant.
That's the one. Planck's constant, H, this incredibly tiny but crucial number. It tells us energy isn't smooth. It comes in these discrete packets, these quanta.
Right, like tiny energy bullets.
Kinda, yeah. And since frequency and wavelength are inversely related through the speed of light,
Right.
C, you can also write the energy as E equals hc divided by E.
Okay, go. So higher frequency or shorter wavelength means more energy per photon.
You got it.
So that implies there must be a minimum frequency, a sort of energy floor needed to knock an electron out.
Exactly. That's the threshold frequency we talk about, usually called F.
F0.
Right. It's the lowest frequency of light that can possibly cause photoemission for a given material. If your light's frequency is below FeO, nothing happens. Doesn't matter how bright the light is.
No electrons come out.
None. The photon energy, HF0, at that threshold frequency is exactly equal to the work function.
Kind of F equals, okay.
And similarly, there's a maximum wavelength, the threshold wavelength, any wavelength longer than that, and the photons just don't have enough energy. Cheer equals.
So you need light that's blue enough or has a short enough wavelength.
That's a good way to think about it. It's like needing a running start to jump over a hurdle. If your speed, your frequency is too low, you just won't clear it no matter how many times you try.
So this explains that weird observation, right? That a really intense beam of, say, red light might do absolutely nothing, while even a very dim ultraviolet light could start kicking out electrons.
Precisely. That was one of the big puzzles classical physics couldn't solve. And it leads us straight into Einstein's, masterpiece on this, the photoelectric equation.
Okay, let's have it. What does the equation tell us?
It's elegant. It says Ke max, the maximum kinetic energy of the ejected electron.
The speed it flies off with, basically.
Well, kinetic energy, yeah. Ke max equals HF minus.
Energy and minus energy needed to escape.
Exactly. Or using wavelength, Ke max equals HF minus.
Okay.
And the truly revolutionary part here is what it tells us about that maximum kinetic energy. Look, it depends directly on the frequency of the light.
Higher frequency, more leftover energy for speed.
Right. But crucially, notice what's not in the equation.
The intensity, the brightness.
Exactly. The maximum kinetic energy of the photoelectron doesn't depend on how bright the light is.
That still feels a bit strange intuitively. You'd think brighter light, a stronger beam, would give the electrons a bigger kick.
And that's the classical way of thinking. Thinking of light as just a wave, where more intensity means a bigger wave amplitude, more energy delivered over time.
Yeah.
But Einstein's quantum picture says, no, light comes in these packets, photons. Each photon interacts with one electron.
One photon, one electron.
Pretty much. So increasing the light intensity just means you're sending more photons per second. More photons mean more collisions, so more electrons get knocked out. But each individual photon still only has energy HF. So the maximum energy any single electron gets kicked out with stays the same, determined only by F and S.
So more photons, more electrons, higher frequency photons, faster electrons.
You've nailed it. It's like throwing more ping pong balls at a window doesn't make each ball hit harder. It just means more balls are hitting it. To make them hit harder, you have to throw each one faster.
That makes sense.
Huh.
Okay, so the generation mechanism is clear now. What about the photoelectrons themselves? Once they're free, what are their defining characteristics?
Right. Good question. They have several key properties we can look at. First off, as we just discussed, their kinetic energy.
Ke.
Yeah. And Einstein's equation gives the maximum Ke. In reality, they come out with a range of energies.
Oh, why is that?
Well, Ke max is for an electron right at the surface that absorbs the photon and escapes cleanly. But electrons can start from slightly deeper energy levels within the material, or they might bump into other atoms on their way out, losing a bit of energy. So you get a spread from almost zero energy up to that Ke max value.
So not all ejected electrons are equally energetic.
Correct. Then there's the number of photoelectrons.
All right, how many come out?
And this we often measure as an electrical current, the photocurrent. And this is where the intensity of the light really matters.
Okay.
As long as your frequency is above the threshold, FF euros, the more intense the light, meaning more photons hitting the surface each second, the more electrons get knocked out per second.
So photocurrent is directly proportional to intensity.
Exactly. More photons in, more electrons out. Simple relationship, that one.
Makes sense. What else characterizes them?
Another really key aspect, and one that supported quantum theory, is the instantaneous emission.
Instantaneous? How fast?
We're talking incredibly fast, like on the order of 10 Qingyu seconds, a nanosecond. The moment a suitable photon hits, the electron comes out. There's practically no delay. This flew in the face of classical wave theory, which predicted that, especially for dim light, an electron would need time to gradually absorb enough energy from the wave before it could escape.
But it doesn't wait. It's immediate if the photon has the energy.
Exactly. Big win for the quantum idea.
Okay, that speed is amazing. What about where they go, the direction they fly off in? Is it just random?
Not entirely random, no. The angular distribution, the direction they're emitted, can actually tell us things. It can be influenced by, say, the polarization of the incoming light.
Like the orientation of the light wave?
And the angle the light hits the material, and importantly, the material's own internal electronic structure.
The way electrons are arranged inside?
Precisely. How the electrons are organized in terms of energy and momentum within the material. This directional information is actually super useful. It's the basis of a technique called angle-resolved photoelectron spectroscopy.
ARPs.
ARPs. Okay, we'll probably come back to that.
We will. It lets us map out that internal electronic structure. Cool. You also mentioned spin, I think.
Yes, spin. Electrons have this intrinsic quantum property called spin. You can loosely picture it like a tiny spinning top, and it gives the electron a magnetic moment.
Like a tiny magnet.
Kind of, yeah. And the really interesting thing is, when an electron is ejected as a photoelectron, it often remembers what its spin state was back in the material.
It carries that information out with it.
It does. And this has led to techniques like spin-resolved photoelectron spectroscopy, allow scientists to probe the magnetic properties of materials right down at the electron level.
Okay, so these photoelectrons, they're not just like identical ejected particles. They carry a surprising amount of information about where they came from, energy, direction, even spin.
Exactly. They're like little messengers from the materials electronic world.
Right. Which leads perfectly to the big question. Why should we, or, our listeners care? What's the payoff? What are the practical uses of all this?
Ah, yes. This is where it gets really exciting, I think, because understanding this fundamental science, the fact that light kicks out electrons and we can analyze them, it's led to a whole toolbox of amazing techniques and, frankly, world-changing technologies.
Okay, like what?
Well, top of the list has to be photoelectron spectroscopy, PES. We already mentioned ARPs and spin-resolved Ps as flavors of this.
Right.
Broadly, PS covers techniques that are very surface sensitive. They let us figure out what elements are in a material.
The composition?
Yeah, the elemental composition.
Yeah.
But also the chemical state, how those elements are bonded, and that detailed electronic structure we talked about.
So it's like a super-powered microscope for the surface chemistry and physics.
That's a great way to put it. A microscopic detective kit. And within PS, a real workhorse technique is X-ray photoelectron spectroscopy, XPS.
XPS, okay, uses X-rays.
It does. You hit the sample with X-rays, which have enough energy to knock out core-level electrons.
Not the outer ones, but the ones closer to the nucleus.
Exactly. The tightly bound inner shell electrons. Now, by carefully measuring the kinetic energy of these ejected photoelectrons.
Using KE max equals HSF.
Yeah, well,
rearranged.
Precisely. We know the X-ray energy, HF. We measure the kinetic energy, KE, so we can calculate the energy the electron had when it was bound its binding energy. And that binding energy is like a fingerprint.
A fingerprint for the element.
Yes. It's unique to each element. But even better, it's slightly shifted depending on the chemical environment around the atom.
Like whether it's an oxide or a pure metal.
Exactly. It reveals the oxidation state, what it's bonded to. Yeah. So XPS tells you what's there and how it's there chemically. Hugely important in materials science, developing catalysts, understanding corrosion, loads of fields.
I can see that. Knowing the exact surface chemistry must be critical. What about other kinds of PES?
Well, then there's ultraviolet photoelectron spectroscopy, UPS.
Uses UV light instead of X-rays.
Right, lower energy photons. These mainly kick out the valence electrons.
The outermost ones. The ones involved in bonding and electricity.
Those are the ones. So UPS is brilliant for probing the valence band structure of materials. It gives you information about molecular orbitals in molecules or the electronic bands in solids that determine if something is a conductor, semiconductor, or insulator.
Okay, so XPS for core electrons in chemistry, UPS for valence electrons and bonding conductivity.
That's a good summary. And then circling back to RP's angle resolved P.
Where the direction mattered.
Exactly. RP's measures both the kinetic energy and the angle the electron comes out at. By doing that, you can actually map out the electronic band structure directly.
What does that mean, mapping the band structure?
It means you get a picture of how the electron's energy changes with its momentum inside the crystal. It's like getting the circuit diagram for the electrons in a solid.
Wow.
It's fundamental for understanding conductivity, how electrons move, and it's been absolutely crucial for studying things like high-temperature superconductors.
Trying to figure out how they work.
Yep. RPs gives us vital clues.
Okay, these spectroscopy techniques are clearly powerful for analysis, but what about applications where photoelectrons do something, rather than just being measured?
Oh, absolutely. The impact goes way beyond just analysis. Think about photomultiplier tubes, PMTs.
PMTs, they detect very faint light, right?
Incredibly faint light. They're used everywhere. Medical diagnostics like PET scanners, particle physics experiments looking for rare events, telescopes staring at distant galaxies.
How do they use photoelectrons?
They start with a photocathode. That's a material chosen specifically because it easily releases photoelectrons. When light hits it, it has a low work function.
Okay.
So a single incoming photon hits the photocathode, releases one, maybe a few, photoelectrons.
One. That's not much signal.
But then comes the amplification. That initial electron is accelerated towards a series of electrodes called dinodes. When it hits the first dynode, it knocks out more electrons.
Like a cascade.
Exactly. Those electrons then hit the next dynode, knocking out even more, and so on. You get this massive multiplication, turning one initial photoelectron into a detectable electrical pulse of millions of electrons.
So one photon can trigger a measurable current? Amazing.
It really is. Allows us to see single photons.
What about solar panels? Do they use this?
Solar cells or photovoltaic cells?
Yeah.
Well, the main effect there is the photovoltaic effect, which involves creating electron-hole pairs at a semiconductor junction.
Okay, slightly different.
It is different in the mechanism of current generation. But the very first step, it's still a photon being absorbed and exciting an electron to a higher energy level. That initial absorption and electron excitation is fundamentally linked to the same physics as the photoelectric effect. It's light energy giving an electron a boost.
So the photoelectric idea is still part of the initial energy capture.
Definitely the underlying principle of light converting to electrical energy starts there.
And our cameras, digital cameras, phone camera.
Absolutely central there. Charge-coupled devices, CCDs, and CMOS image sensors. The chips that capture images in nearly all digital cameras and telescopes, they rely on the internal photoelectric effect.
Internal, meaning the electron doesn't leave the material.
Exactly. Photons hit the silicon pixels in the sensor. They generate electrons within the silicon, but the electrons are collected within the pixel itself.
Okay.
The number of electrons collected in a pixel is directly proportional to how much light, how many photons hit that pixel.
More light, more electrons stored.
Yep. Then the camera reads out the charge from each pixel, and that pattern of charge becomes your digital image. So every single dot in your photo started as photoelectrons generated by light.
Mind-blowing. Our whole visual digital world rests on this effect.
Pretty much.
What about seeing in the dark? Night vision.
Good one.
Okay.
Yes, many night vision devices also rely on this. They often use a photocathode, just like a PMT.
Okay.
It absorbs the very faint ambient light, maybe even some infrared light that we can't see.
Converts it to photoelectrons.
Converts it to photoelectrons. These are then amplified, again, often using similar principles to PMTs or microchannel plates, and then they're slammed into a phosphorus screen.
Which glows.
Which glows green, usually, creating the visible image you see through the goggles. So turning invisible light into electrons, amplifying them, then turning them back into visible light.
Incredible. From fundamental physics to seeing in the dark. Okay, this has been quite the journey. Let's maybe try and summarize the absolute key takeaways for everyone listening.
Sounds good. So, takeaway number 1. Photoelectrons pop out when light with enough energy hits a material. Solid, liquid, gas. Doesn't matter.
And that enough energy part is key. It's governed by the photoelectric effect. The photon's energy has to beat the material's work function.
Exactly. And crucially, the maximum kinetic energy of those ejected electrons, how fast they move, depends on the light's frequency, its color, not its brightness.
Right. Higher frequency means higher max KE. But the number of photoelectrons, the photocurrent, that depends on the light's intensity, the brightness.
Correct. More intense light, above the threshold frequency, means more photons, which means more electrons kicked out per second.
And we saw how incredibly useful studying these electrons is. Techniques like XPS, UPS, ARPS, they let us probe materials right down to the atomic and electronic level.
Absolutely essential tools for materials, science, chemistry, physics.
Yeah.
Understanding what things are made of and why they behave the way they do. Designing new materials, too.
And then the technologies. PMTs for detecting faint light, the basis of solar cells, the sensors in every digital camera, night vision.
Yeah.
Photoelectrons are working hard out there.
They really are. It's a perfect example of how exploring a fundamental physics puzzle leads to technologies that completely reshape our world.
It really drives home how much our modern tech relies on understanding quantum mechanics, doesn't it?
Without a doubt. And the study isn't over. People are still researching photoemission, exploring new materials, refining techniques. It's still a very active field.
Well, this has been genuinely illuminating. A fantastic deep dive into the world of photoelectrons, from Einstein's insight to the sensors capturing this conversation, probably.
Yeah, quite possibly.
It really makes you appreciate how understanding these tiny fundamental interactions has such massive consequences.
It does. And maybe that leaves a final thought for you, our listener. Just take a moment to consider how many devices and technologies you rely on every single day.
Mm-hmm.
How many of them, deep down, trace their origins back to understanding how light and matter interact at this quantum level, this photoelectric dance, and then maybe wonder, what comes next? What other breakthroughs might be waiting as we keep probing these fundamental secrets?
A fascinating question to ponder. Thanks for joining us on the Deep Dive.